Hi everyone, thanks for watching. In this video we're going to take a look at the bonding that takes place between metallic atoms. So first, remember that in ionic bonding you need a metal atom to transfer its valence electrons to a non-metal atom. Like between sodium and bromine, the valence electron moves from sodium to bromine. You form a +1 and a -1, and because of the opposite charges they're attracted to each other. That's the ionic bond. This video asks the question, what about if you didn't have a nonmetal present that was willing to gain electrons? What if the bromine wasn't there? Or what about if the only other atom that was there was another metal, say another sodium atom? This second sodium atom is just like this one. It doesn't want to gain electrons, it will only lose them. Or think about a gold ring, any other solid chunk of metal where there's only metallic atoms. How are all those atoms being held together? Or in this case, with our sodium atoms, a solid chunk of sodium. If there's no non-metal and only metals, what are these atoms doing? So to explain the metallic bonding that takes place in a sample of pure metal like this, let's first add in some more sodium dot diagrams, because of course there's not just two atoms in here, there's a ton of them. Now the first important part of how these metal atoms bond to each other is kind of just a repeat from ionic bonding. Just like in that scenario, metal atoms lose their valence electrons, and these guys are going to do the same thing. The difference is there's no non-metal to give those electrons a place to go, so here the valence electrons don't really go anywhere. Instead, those valence electrons are said to be delocalized from their original atom, and we'll show you what this looks like in a second. And they just become free-flowing, which means they can move around amongst all the other metal atoms in the sample. What that might look like if we start with this atom right here, it's just going to lose its valence like any other time, except that valence electron just now kind of has the ability to move in and around all these others. That atom also gets a +1 charge because it has lost an electron, just like in ionic bonding. And the next sodium atom is going to lose its valence, getting a +1, and the same thing with the next one. It'll lose its valence, getting a +1. They will all lose their valence electrons, all attaining +1 charges. So here's a slightly more accurate version of what this might actually look like if we could see it. Notice we've got our electrons that are now moving, free-flowing, delocalized, no longer belonging to the original atom they came from, free to move in and around all the other metal atoms in the sample. We've also got metal atoms which are all positive because they've lost electrons, so they're all cations. Also notice that those cations have fixed positions, which means they do not move even though the electrons are moving. This positive ion is next to this one and they're not changing positions even though they do vibrate a little bit. This has a name. Sometimes you might see this called the Sea of Electrons Theory, because the electrons can flow in and around the cations just like water flows in the ocean. So now we're probably in a pretty good place to summarize this metallic bonding. We've got metal cations, and those cations are held in place by their attraction to the delocalized valence electrons that surround them. And all that's really happening here is we've got these negative electrons that surround some positive metal atoms, and because opposites attract, those negative electrons kind of act like a glue that hold all these positive particles together. That concludes this video on metallic bonding. Thanks for watching. Here's a brief summary.